Let us find out potential due to a system of charges. It simply means that there are more than one charges, that is Q1, what you can see here, then Q2, Q3, Q4 and Q5. So there are more than one charges and we have to find potential at the point P due to these charges, right? Earlier we used that our charge, the point charges are at the origin, okay? But here there is a little bit of change that these charges are not at the origin. Origin is somewhere here, okay? This is our origin, and from the origin R1 is Q1 is R1 distance away, okay? Or the position vector of Q1, the charge Q1 is R1, okay? This is the position vector of charge Q1. So, and that for Q2 is R2, okay? And the same way for Q3 it's R3, and so we have to think about these position vectors also on the one side, okay? And what we really need to find out that these charges, due to these charges there will be potential at the point P, okay? And what is this potential? It is actually, suppose at infinity, this is our infinity, there is one test charge, okay? One test charge like 1 coulomb, and we have to bring this charge from infinity to the point P, and the work done in bringing this charge from infinity to this point, okay, is our potential, okay? Is the work done per unit charge is potential. So you have to understand this concept that at point P, if we want to find the potential, it is just the work done in bringing a unit positive charge from infinity to that point, okay? And everything is set up now, like we have position vectors of the charges, and also from the point P, what you can see here, the distance of the charge Q1 is R1P, okay? These are the distances. So for Q2 it is R2P. That's it. This is all we need to set it up, and after that it is very easy to find the potential at a point P due to charge Q1, which is simply, you know, that potential due to Q1, if we write it as V1 is equal to 1 upon 4 pi epsilon naught the charge Q1 divided by the distance between the charge and the point where we have to find the potential, that is P. So that distance is R1P, and that is our potential due to one of the charges. And then the second is potential due to charge Q2 is V2 is equal to 1 upon 4 pi epsilon naught Q2, the charge Q2 upon R2P, and so on, okay? There can be many charges and many potentials, individual potentials will be there. Then we can simply apply the superposition principle, okay? Here we are not considering the vector part. Why? We are only considering the distance between these 2 points, point P and the charge, wherever the charge is. So we are not considering the vector because potential is a scalar quantity. So okay, so we will use the superposition principle, which says that we can actually do the sum of all the potentials to find the total potential due to many charges or the system of charges at a point P, and we'll simply add these. So this is the algebraic sum of the potentials due to individual charges, okay? And that is simply is equal to, total potential is equal to 1 upon 4 pi epsilon naught Q1 upon R1P plus Q2 upon R2P plus Q3 upon R3P, and so on up to Qn divided by Rnp. So there can be n number of charges. Briefly, we'll touch upon one another concept here. That is, so far we have talked about point charges. Okay. Then there is a condition that when the charge distribution is continuous. Okay, we have done that in chapter 1. So for example, we talk about one sphere, and the charge Q on this sphere is actually spread continuously. So charge is distributed everywhere. And our charge density is rho. Okay, and what is this rho? Rho is actually charge upon the volume. Okay, so it is delta Q upon the volume delta V. Then we take one small volume. This volume is delta V. On this delta V small volume, the charge here, the charge is rho, charge density multiplied by delta V. So this is the charge for the small volume delta V. And due to this, the potential at point P, okay, which is r distance away from that small volume delta V, okay, is what? Is potential at P is 1 upon 4 pi epsilon naught. And Q, the charge we have to put, and our charge is rho delta V. So rho delta V upon R. All right. Here think about a condition that this sphere is far, very far, and from the point where we have to find the potential. Then what happens? Potential due to, or the total potential due to all the volume elements in this sphere, all the volume elements, is actually adding up all the charges, and total charge on this volume or this sphere is Q. Okay, so then it will be actually V is equal to 1 upon 4 pi epsilon naught Q. Total charge is Q upon R. Simple. Just looks like a point charge, though it is continuous. Alright, so let us try to understand it in another way. So now think about this sphere. Okay, so I can draw only half part of the sphere because we need to use the space on the left. So let's say the radius of this sphere is R, and we know that the total charge spread in this sphere is total charge is Q. So the volume at P, at a point P, so let it be this point P, and the distance of this point P from the center of the sphere, because we believe that whole charge is concentrated at the center. Okay, though it is spread continuously, but we believe that if it is very far, then the distance is small r from the sphere to the point P where we want to find the potential. So volume potential is given by 1 upon 4 pi epsilon naught Q upon total charge upon R, this R. Okay, but when we come close to the sphere, so let's say the potential here, or like when we come close, potential at this point, and then even come close, or even maybe at the surface. If we come at the surface, then potential is simply V is equal to 1 upon 4 pi epsilon naught Q upon small r, but small r is now equal to the capital R, the radius. So that's why R is usually greater than the radius. Small r is usually greater than the radius, but it is also equal to radius if we really want to find the potential at the surface of the sphere. Okay, so this is it. This is all you need to know. And this is the case when there is a uniform charge spherical shell. Okay, so if the sphere is hollow inside, then this condition fulfills. Okay, and so in this situation, what happens? Electric field inside the shell is zero. Electric field inside the shell is zero because the charges are actually spread on the sphere, because metal is outside. So what are our outcomes? That potential at the surface of this electric shell is V is equal to 1 upon 4 pi epsilon naught Q upon R, capital R, that is the radius. And if we go far from the spherical shell, then the potential is V is equal to 1 upon 4 pi epsilon naught Q upon small r. Okay, and this brings us ready to understand the next topic, that is equipotential surface, that we will cover in the next video. Thank you.